In this video, we're going to go over reactions of monosaccharides. Now, it's helpful to talk about the way we've been analyzing drawings of monosaccharides. So far, we have been looking at Fisher projections of monosaccharides. Now, in a Fisher projection, we draw the linear version of a monosaccharide, where the carbon chain is the carbons written in a vertical line going down, right? And so to abbreviate that, we can just draw a straight vertical line. Let's say we're looking at one of these aldose sugars. In that straight vertical line, the very top point can be our first carbon, and it can be double bonded to an oxygen and have a hydrogen on it. So since it's a C, double bonded to O with an H, that's our aldehyde or our aldose sugar. And then every intersection after that represents a carbon. So, if we draw an H on the left and an OH on the right of that horizontal line, the carbon, the intersection in the middle represents a carbon. And we can just keep doing that. So I'm just going to kind of redraw this first Fisher projection just to kind of, give us an idea. What are we talking about? So we can draw them just like this as straight lines. Biochemists like to do this because they find it a little easier to look at the geometry around these chiral carbons. If we have a straight line and we're looking at, for example, the OH on the right, like we call that our D versus L, stereochemistry. So that's one reason that is done. Okay, and so again, every intersection just counts as a carbon. So here's 1, 2, 3, 4, 5. There's 6 carbons as we go down that chain. So we first have, again, C double bonded to an O with an H. Then we have C with OH on the right, C with OH on the left, C with OH on the right, C with OH on the right, and CH2OH. That last OH is on the right, and it makes it D. The first one was that C double bond OH, which makes it our aldose sugar. So just kind of reviewing, where does that come from? Fisher projection. So I said we were going to get into reactions. Well, what does oxidation of an aldose look like? Okay, well, we could oxidize. We could use a strong or a weak oxidizing agent. In our labs, that's been a dichromate. The weak one could be our Benedict's reagent. That is what we commonly, are using to oxidize sugars. We would leave the whole backbone the same and just change our first C double bond O with an H to an OH at the end for an aldehyde. But then the rest of the sugar, our OH on the right, our OH on the left, our 2 OHs on the right, they would all be unchanged. So we got our vertical line, and then we draw our horizontal lines across that with OH on the right, left, right, right, CH2OH. So again, we got our vertical line here. We got our horizontal lines to show where we're going to have carbons at each intersection. We have C double bonded to an O with an OH first. Then we have, as we go down, OH on the right, left, right, right, CH2OH. And again, our carbons are 1, 2, 3, 4, 5, 6 at those 6 intersections. So that's our hexose, right? So if we were trying to look at what kind of sugars we had, well, we had a hexose. Again, we had our hexose to start, and then we oxidized all the way to a carboxylic acid. So from aldehyde to carboxylic acid. What about reduction of an aldose? We could actually do reduction. And, we've done reduction with hydrogen and a catalyst, like a metal catalyst like nickel. So how would we reduce this? Well, we would reduce the aldehyde of the aldose. We would keep everything in the chain the same except for that first C double bond O with an H, where that aldehyde would become C bonded to two H's and an OH. So we're just reducing that. We're going to keep everything else the same. So with the next line, we're going to have OH on the left, or excuse me, on the right. We have an OH on the left. We're going to have two OHs on the right. And somehow I've run myself out of room. Two OHs on the right, and down at the bottom, I should have had CH2OH. So what I have done is reduce my aldehyde to an alcohol. And these are where we get sugar alcohols from. So let me see if I can just kind of change this to give us some good labels here. This would be an example of a sugar alcohol. Okay, because here's our alcohol with our sugar backbone. And these are sugar substitutes, things like sorbitol, xylitol, that you may have heard of in everyday life. By the way, these are typically toxic to pets, so you don't want your pets exposed to these. Toxic to a pet. But you've taken your sugar, like your aldose, and you've reduced it to an alcohol. And it's where we get some of these sugar alcohols, like sorbitol, like xylitol from. It's kind of interesting. Okay, now we want to look at what can happen with our Fischer projection. So our alcohols are only in these straight chain Fischer projections. When they're in a solid form, in a dry, what's like referred to as a dry form, and they're in an equilibrium, and especially in an aqueous solution, they will actually tend toward a cyclic form. So here we've got our example Fischer projection. So this is glucose, by the way, and it is helpful to be able to recognize glucose. That is one of our learning outcomes, but we have it's an aldose, it's a hexose sugar. So we've got our aldehyde functional group, our C double bond O and an H for our first carbon. Our second carbon has the OH on the right. Our third carbon has the OH on the left. Our fourth carbon has OH on the right. Our fifth carbon has OH on the right. That's what makes it D. And then our sixth carbon is our CH2OH. So again, this one's actually glucose. So as I was saying, we've been looking at glucose since our first slide with our apple example. We were talking about how we could oxidize it with a Benedict's reagent and how that made it a reducing sugar because it reduces the Benedict's. So we've seen oxidation of it now. We've seen reduction of glucose. Here, when we talk about glucose in solution, it's going to be in equilibrium, pushing towards its cyclic form and have preference actually for a cyclic form instead of this straight chain Fischer projection. So it has, equilibrium between this and a cyclic form, and the cyclic form has the name Haworth projection. So this is actually referred to as a Haworth projection or the cyclic form. And it's going to prefer to be in that cyclic form whenever it's in solution or have a much higher percentage in the cyclic form, especially in solution. But it is an equilibrium or a back and forth. Basically what happens to make the cyclic form is in order for the aldehyde carbon to be able to form a bond to that DOH, the O that makes that OH that makes it a D form. Well, that aldehyde carbon has to bond to that oxygen, and the hydrogen that was on that OH essentially has to be hydrogen added to the carbonyl oxygen, to that C double bond O oxygen. That's going to have to get this hydrogen that was originally on the D OH, that second to last OH, the one that's always on the right. That hydrogen has to be, form a bond to the carbonyl oxygen, and one of those carbonyl oxygen bonds has to break. Suffice it to say that it's going to want to be in this cyclic form versus in the Fischer projection when the sugars like glucose are in solution.